My 6-year-old daughter is fascinated with prediction problems. And one of the things that she does with me, every once in a while we play this game where she asks me to predict what she's going to do in the next 10 seconds. And after hearing my prediction, she'll do exactly the opposite of whatever I predicted. And then she'll have a really good laugh at it. Okay? I try to convince her that, look, you have some agency, you have free will. And more importantly, you also know what I predicted, so you can always prove me wrong. But then she has fun anyway. Okay, now this seems like a very trivial problem or a trivial sort of a case of AI not working or prediction not working. But surprisingly enough, the giants of AI have made similar mistakes. In 2014, Microsoft, as you probably know, released this chatbot called Tay, which they marketed as the AI with zero chill. Okay, it started very nicely. It was a 19-year-old girl's avatar, and she was tweeting very nicely. Within 16 hours, this started happening. She started saying all kinds of things because the people who were playing with her were starting to game her and trying to talk to her, and eventually within 16 hours Microsoft said enough of this and they shut down the service called Tay. Okay. They had actually tried this in China with a different name, and that was very successful. So they thought doing it in the free world is going to be easier, but actually it wasn't. It was really hard, and that's the story of a failure of AI because it does not predict how actually humans will play with it. It's an AI failure. Let me give you one more AI failure that you're very familiar with, probably have experienced yourself. Back in 2009, when Siri was launched, it did all kinds of things that were really funny. But because the AI wasn't good enough, right? Now, so these are several examples of AI failures in our own world. I'll give you one that we did, trying to work with with a healthcare player and trying to predict who are the people who are not going to take their drugs on time. And our idea was to go and reach out to them so that we can improve their medication adherence. What we did with all the analytics and AI that we brought to the table, we could not see any pattern beyond saying that people who don't take their drugs on time are going to continue to not take their drugs on time. We couldn't find anything more interesting than that, and that was it. So our AI did not really work. So there are a number of different AI failures, but the idea behind AI is, can we build algorithms that can match or exceed human performance in a broad range of cognitive tasks? That's been the sort of idea behind AI. Right? So we've talked about a couple of AI failures. Let me see some more failures and then talk about what else failed in solving that kind of a problem. Before going there, however, I want to tell you that while Siri failed in 2009, and it could have led to people thinking, no, speech recognition is not very good because Siri did not understand accents and so on. The people who did not invest behind that, they did struggle because in 2014, suddenly the speech recognition error started dropping and the adoption just took off. So people who thought, yeah, it's too new, let's not invest in the speech recognition technology, suffered, and the ones who invested succeeded. So yeah, so there's a caveat there. Yes, AI fails, but it's important to explore and exploit and experiment. Now let's take another example of another such failure. In 2014, Google launched Google Flu Trends. You're probably aware of that. They looked at all the kinds of data, search data, and they could accurately predict flu trends in different parts of the world, local markets in the world, weeks in advance of the World Health Organization and others. They started releasing this data. It was very successful. There were a lot of case studies written on it. In fact, Ken's book actually talks about that as a success story. Right? A few months later, it actually started failing because Google's own product changed. They started doing autofill. They started suggesting your search features. The product changed, people's search patterns changed. When the underlying data started changing, all the forecasts, all the prediction models just miserably failed. Yes, there was clearly an AI error there, but there was also a data error, lack of understanding of the fact that underlying data changed so rapidly. In fact, Google shut it down in 2015 because it was completely erroneous. Right? So that's an example of failure of, in my opinion, engineering. The aspect of data engineering, the idea that underlying data has to be stable with the underlying data, was something that Google missed. Take another example of this is essentially the idea of engineering is how do we seamlessly connect data pipelines and automate decisions in real time. The data, underlying data for Google changed. They're a really strong engineering company, but certainly the underlying data changed and they failed. So the second types of failure is about engineering failures. The third set of failures, I want to again take Google as an example. Google is one of my favorite companies, but they have a bunch of failures that are interesting to talk about. Google launched something called as Google Wave in 2009. Any of you used it by any chance? It was supposed to be the next best thing in collaboration. It's some outstanding innovation. Unfortunately, within a few months, they shut it down because it was horribly difficult to use. Look at how convoluted and cumbersome the user interface was for this. Right? Take another example of Google's own innovation in Google Glass. They started to. This was a very touted invention. It came with $1,500 at a price tag of $1,500, invite only, and people who started using it, they started seeing resistance from other people who were not using it. They didn't like the idea that people started throwing such people out of the restaurants because they were like, why are you taking my pictures? Why are you using these Google Glass? And it was not very clear what problem Google Glass was actually solving. And eventually Google shut it down. Another example of failure, but in this case, in my opinion, it's a design failure. The idea of solving the right problem and having a deeper understanding of human behavior. So we've talked about three kinds of failures: the AI failures, engineering failures, and design failures. And our idea is how do we bring them together so that we can solve problems. And before we go there, I want to give you an example, a very fascinating example of a success that came up only last week. Last week, OpenAI released a new program, and this is what they did. They basically wrote they gave machine learning software 40 GB of internet text, okay, and they trained the algorithms to understand the 40 GB of internet text and to predict the next word. If you give them a set of words, it predicts the next word in that sequence, okay, and then after training that model, they gave it the following sentence. Okay, this is a story. They started writing the story. This is a human input. It says, in a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. Okay, that's it. Now, this is what the machine did after 10 tries. Take a look. This is real, by the way. The scientists named the population after their distinctive horn, Ovid's unicorn. These four-horned silver-white unicorns were previously unknown to science. Now, after almost 2 centuries, mystery of what sparked this odd phenomenon is finally solved. Dr. Jorge Perez, an evolutionary biologist from the University of La Paz, and several companions were exploring the Andes Mountains when they found a small valley with no other animals or humans. Perez noticed that the valley had what appeared to be a natural fountain surrounded by 2 peaks of rocks and silver snow. And the story continues, completely written by AI. A fascinating example of what kind of magic is beginning to happen in the areas of AI. Another sort of really fascinating example that happened only a few weeks ago is this video, okay, and watch this video. There are 2 people here. That is Steve Buscemi, who's a famous Hollywood actor in many, many movies, and there's Jennifer Lawrence. And this is
Sheridan Watson from BuzzFeed right here. Hi. So you're a huge Bravo
This is a Golden
fan.
Globe.
Oh, Who is your favorite and least favorite housewife of all cities?
There's a Jennifer Lawrence body and Steve Buscemi's face.
My favorite
and
is probably
the video.
Lisa Vanderpump. My least favorite, I don't want to have to say. I mean, I don't want to have to say because who knows when you're going to run into these people, you know?
Jennifer, over here to your right.
I hope I don't. I hope I'm never in that like situation where I'm like, all the housewives are here. Anyway, actually, I take that back. I do want to be in that situation.
Jennifer, over here.
Yes,
to your
Sam
right.
Smith? Oh, sorry. Yeah.
So what you can see here is near perfect rendering of video in real time.
Yeah, but then
This technology is called deepfake, as you're probably aware of that. This is using deep learning to fake videos. Of course, deep learning is already being used to fake images, but it's now beginning to get so good that you can actually fake complete videos. So you will not be able to trust what you see on video form anymore because deep learning is becoming that good. In fact, it's becoming so good that AI is becoming so much better that I do believe that AI will become ubiquitous. Back in the day, when computing became good and cheap, right? We started putting computer chips in everything, right? Every problem became a computing problem. Now every problem will become a prediction problem or an AI problem, and we will reframe problems as AI problems, as Ken also mentioned, and the cost of AI also will dramatically drop, which also Ken mentioned. However, I do believe that AI won't be enough. Just super intelligence or or ability of algorithm to outperform humans in a task is not going to be enough to solve problems at scale. What will we need in that world? You've seen what happened with Tesla. When Model 3 was launched, they were struggling to deliver their cars on time. They were horribly behind. The stock suffered. So many different things happened, and eventually Elon Musk tweeted this. He believes that excessive automation at Tesla was a mistake. To be precise, his mistake, and humans are underrated. Now, what happened here? What happened here was they tried to automate everything. They really tried to automate everything. They had the whole set of machines with no human intervention building this Model 3. But whenever they had to change anything, any flexibility that they need in the system meant reworking the whole thing, right? And that's why he realized that excessive automation wasn't working, and dumb automation really doesn't always solve problems. You may have heard a lot about robotic process automation lately, and everybody thinks that's the next thing after sliced bread, right? It seems to have solved all problems. Unfortunately, most of it is really dumb automation. And when you have dumb automation, it means that it's not flexible. The moment you change anything, everything fails, okay? And then you have to reprogram it. One way to think about what to automate and what not to automate is this framework. On the x-axis here, you see the complexity of what problem you're trying to solve. And on the y-axis is the complexity of sense making. Humans, in general, are really good at sense making. We're able to take a lot of different things and make sense of that. Machines, not so. Machines are really good at solving a problem where the problem is very, very clear. Now, as you move from sort of industrial age to more of information age to more of the AI age, you can see that yes, we have been increasing our ability to handle higher sense making and mission complexity, but there is always a huge sort of area beyond that realm, which is machine realm, which is a human realm, where human judgment is important, human sense making is important, as simple as common sense. Some of the failures of Tay and others that you saw were because simple common sense was not involved. Why did automation at Tesla fail? Because humans can quickly adjust to a new reality. Machines take a long time, right? And the other important part is as the overall complexity increases, cost dramatically increases as well. And because of these two reasons, you have to pick what to automate, what not to automate, and then accordingly make those choices. Right. Let me give you one more example of, so this is a failure in terms of what to automate and what not to automate. Recently, we started working with one of the largest tea manufacturers in the world, and we were trying to improve the quality of their forecasts, and our goal was to increase the forecast accuracy by at least 5 percentage points, because they have been using some sort of traditional forecasting techniques. So what we did was we brought in new age AI techniques, deep learning, machine learning, and so on. And what we showed them in the first pass was that in UK, where it's a very competitive market for tea, very promotion sensitive, and when you have to forecast at the SKU level, at a retailer level, it's really difficult. We showed that we could actually improve the forecast by 8 percentage points. Very excited. We said this is a great example. Now then, so once we did that pilot, our next problem was how do we do this for the whole world? But the problem framed to us was there are a whole bunch of demand planners, and you have to build these forecasting models so that we don't need the demand planners anymore. We may or may not need the demand planners, but I want you to beat the demand planners. That was the question that we were trying to solve. Now, we started realizing after some time that it was hard to beat the demand planners. And we were thinking, what's going on? I mean, we have such good AI. Why is it that we are not beating the demand planners? The underlying reason is the following. Demand planners have access to a lot more information. They're making phone calls inside the organization. They know supply disruptions happening somewhere. They're able to talk to the retailers. They have access to a whole range of data, sense-making data, that the algorithm does not have. And therefore, when you pit the algorithm against humans, we are actually failing, right? But this is not an AI failure as much as it's the failure of framing the right problem. Our problem was framed as humans versus machines. Our problem was, how do you beat how can the machine beat human performance? The real question here was, how can we improve the overall performance of the forecast, right? We have human intelligence, we have machine intelligence. Are they complementary? Can they together solve a problem better than we solved before? If so, it's worth solving. However, when the problem is framed as humans versus machines, we end up having many such failures. Look at this recent accident that happened in Tesla, right? One of the things that happened here was the driver was actually who was sitting at the wheel. He was watching a video, he was watching a movie, and then a big truck came in, and because the AI could not distinguish between the truck and the surroundings, it was merging with the surroundings, the car kept going and crashed into the truck. The person died, right? In fact, this person was, for 6 seconds before the crash, this person his hands were not on the wheel. He's supposed to have his hands on the wheel. He's supposed to not be doing anything, even though the car runs on its own. It's an autopilot mode, right? It failed and the person died, and we've had many other such situations. So one question, when we have a conversation on this topic, one thing that comes up is, why is such a high standard for machines, right? Humans make errors all the time. Okay, machine made one error, but if you replace that humans with machines, overall we'll save millions of lives as far as driving is concerned, right? That's one set of objections that comes in when we have a conversation like this, right? And the reason it's important is because human beings make errors, but they don't scale. Those errors don't scale. If I make an error of driving, I'm gone, but that doesn't mean I don't kill other people. But if machines make errors, those errors can scale and they can actually kill people, right? The second aspect here is that the machine-human interface wasn't designed very well. Like it is automated most of the time. The car works on its own in autopilot mode. However, there are some times when the car has to hand over to the human to drive. If that doesn't work, things fail. Think about the crash that happened, Air France crash that happened in 2009. AF447 went down into the sea and 238 people died back in 2009. What happened there was the autopilot started malfunctioning. It had some problems because one sensor that was there in some plane was not working. So the autopilot recognized that it's not doing a good job. It said, humans take over, pilots take over, right? When they took over, they had a screen that they had to sort of make sense of very quickly. And by the time they could make sense of what exactly was the problem, what exactly was going on in the plane, they made a set of maneuvers which were the exact opposite of what they should have done. And the plane went down, and that's it. Right? So we have designed human-machine interface in such a way that yes, we think automate everything, but then we haven't thought through of situations where the automation doesn't work and where humans have to take over. We have not designed for this handover from machines to humans, right? So that's another reason why things fail. Now, one more example of failure here is Theranos. We are all very familiar with that. I hope you've read the book Bad Blood, which is a great story of how Theranos failed. They created this design, this machine, good-looking design, and they created this test, tiny drop of blood, which will give you all kinds of diagnostic results. Unfortunately, there was complete overpromise in terms of the technology. It was not going to solve any problem, and we ended up making things simpler than they should be. There are many situations in the world of AI too. For example, take the world of chess, right? Machines could defeat humans in chess just by programming a bunch of if-then-else conditions, right? By telling them, instead of a human who's looking at maybe 100 different scenarios before making a move, the machine could look at 1,000 different scenarios because it's much more computationally faster. But we had taught the machine to look at each sort of each board configuration and rate that configuration, compare millions of options, and then pick the best option. And with just that kind of an AI, it defeated human beings. That same AI could have never defeated a human being in the game of Go. And that's why we had much better AI, because the problem is more complex than that. This simple stuff doesn't work. Simplification beyond what is possible for the problem doesn't work. Okay. Um, one last example here is what we've been doing with in the chest X-ray space. When we built the first set of chest X-ray algorithms to predict various kinds of abnormalities in chest X-ray, one of the things we saw was that these chest X-ray algorithms were very, very good. We could look at chest X-ray and with a very high degree of accuracy, even with a very small data set, find out which of those was abnormal. And while doing that, we realized that there was something funny happening, right? We saw all the ones where we were getting right, but also had some annotations on the X-ray. So what the algorithm was doing was actually picking up the fact that an annotated X-ray with some notes on it, typically tends to be an abnormal X-ray, right? So it picked that trend and fitted that trend and said, hey, you're doing great, right? And when in actual practice, that algorithm would have miserably failed, because in real life, X-rays don't come with annotation before a machine reads them, right? This is the case of overfitting, and these kinds of overfitting tends to happen all the time. There's a lot of overpromise of technology, typically because they are not validated. The results are not validated. So we went back, we fixed, thankfully, we had significantly strong validation protocols. So we built these algorithms, we took these algorithms to a whole host of different hospitals to validate, right? So just to back up a little bit on the problem, right? Why are we interested in chest X-rays? Because today there are hundreds of millions of chest X-rays every year that are taken, and there's a 23% error rate in reading X-rays. Right? So doctors tend to make lots of mistakes here because they're bored, they're busy, they're not interested, and so on. And for example, they miss 19% of lung nodules. So we said, how can we enable the doctor to augment his or her intelligence by giving the chest X-ray automatically, right? So we could look at a chest X-ray and give them something like all these kinds of abnormalities on the chest X-ray. Now that was the idea behind that. So we built these algorithms, but we said, let's go and let's see how they perform in the market, right? So we actually took it to a hospital. These are all published, peer-reviewed, published in peer-reviewed journals. But one of those peer-reviewed journals, what we did there was we took X-rays, 5,000 X-rays, and gave it, which were already rated by, there were a radiologist report already available there. Cure's algorithms sort of scored those algorithms, those X-rays, and we looked at who was right? So in 4,000 cases out of the 5,000, Cure's result and the original radiologist were exactly the same. They both agreed on the findings. So the balance 1,000 were where Cure's algorithm and the original radiologist's recommendation were sort of not the same. So we gave those 1,000 X-rays to a panel of 3 radiologists. Said, look at these, and they were blinded to this, right? So they looked at these independently, and they came to a consensus. These 3 radiologists looked at each of those 1,000 X-rays and came to a consensus and said abnormal or normal. And what we realized from that was the Cure's algorithm was beating the radiologist's 2:1. That's the kind of validation, which means that yes, not only did we used radiologists as the ground truth before building these models, but in the process, we had built an algorithm that was actually better than the radiologists themselves. Right? That's what we took, and now this is being used in a number of different situations to do tuberculosis screening, which I'll come to in a little bit. The other important aspect of using testing, I mean, it's important that there is a culture of experimentation. We built trial run for our own experiments and for clients' experiments, but the idea is that if you want to learn something and do new stuff and understand why things are happening, you need to run controlled experiments, and trial run helps you do that. Now I'm going to skip some of these, lack of time. So eventually, we think if you bring in good AI, strong engineering, and great design, you can solve problems at scale. Okay, let me give you a couple of examples of that. This is an example. This is not a Fractal example, but in 2009, in UCSF Medical Center, one person died because of wrong prescription delivery, and that's when they decided to automate the whole thing. So they built this robotic pharmacy, which looks at a prescription, understands what is to be given, and then picks up the medicines, packs it, and gives it to the patient. The pharmacist now spends time in advising the patient on things like what kind of side effects there may be, what kind of dosage, etc. They spend time in talking to the patients, which they are good at. The machine does the job of picking and packing medicines and understanding exactly what the prescription says and reading those illegible, doctor text usually. That's what it does, right? So great example, because they tried to become very narrow. They took a very narrow problem, tried to solve it through AI engineering and design. They had great AI. They fully thought through the solution from a design standpoint, and certainly good engineering as well. So that's really an example of that. The counter example to this is what Watson has been trying to do, which is to automate whole of medicine. They've been trying to be everything to everybody, over promising, and therefore failing in the same process, right? I'll skip this. Similarly, what we've been trying to do at Cuddle is how do you bring in AI engineering and design to solve problems and help people make better decisions in their own professional lives. Right? We all have Facebook and LinkedIn and others to tell us what we need to know in our private lives, right? What's happening in our social circles. But we don't have that in our business. So we said, here's what you should have. You should have your own personalized dashboard of what's happening in your world, in the world of business. You should know what you need to know. What is the most interesting thing that's happening in your business right now? So mine all the text in the world, all the data in the organization, and tell you exactly what's important to me, what should I pay attention to. And finally, my interface should be so easy that I can ask questions and get answers. I shouldn't have to write SQL queries or do something like that. So that, how do you bring in AI engineering design? This is one example of how Fractal is doing. Now with that, I'll go to the final story of our chest X-ray. I just want you to watch this video for a couple of minutes. What we are doing with tuberculosis with Cure.ai.
Tuberculosis is a disease caused by mycobacterium tuberculosis. It primarily affects the lungs, and if untreated, a person annually can actually spread the TB to 15 other persons. Globally, we have actually 10.4 million cases happening every year. Among that, actually, major chunk of it is almost 4 million is not reported or not identified. So that's a bigger problem we need to crack. If we need to actually achieve the elimination targets by 2035, if you have to prioritize case finding, that's an area where the investment needs to come from. When the patients are actually seeking care to health system, we should not miss at all. There should be zero leakages. So there we should optimize the existing technologies.
TB is a very big problem and it cannot be solved without automation. There's a large difference between TB incidents and the number of cases that were reported. This gap can only bridge with something that is very scalable and which can be automated without manual intervention. So we developed a deep learning based solution that was trained on more than 1 million chest x-rays to develop a solution that can automatically report on the abnormal findings from chest x-rays.
Currently, it takes somewhere around 2 months for the patient to get diagnosed from the symptom. We are using Cure.ai technology to expedite that diagnosis and empower the frontline health doctors to actually trigger and reflex it for further confirmatory testing.
Radiologists can verify in the same portal, and then the organization which is doing the microbiological test can add their data, plug in their data into the same portal. And once you have a dashboard which puts all this information, which collects all this information in one place, it becomes very powerful. The loss itself can be minimized. It becomes that much easier to track the person and make sure that he is getting diagnosed and is receiving the treatment if he is positive for TB. And that's what we are doing. That's what we are doing with our TB solution.